Yeah, thank you, everyone, and welcome to this talk. And thank you for the nice introduction. So yes, my name is Jan Fiala, and I look after the optimization at NAG. Now, let me try to share my screen with the slides and see if it actually works. So hopefully you should see shortly my screen. Does it work? Can you see the screen?
Yes. Yes.
Excellent. Right. When we were thinking what to talk about, it was actually an idea. What if we use the expertise at NAG and the experience and basically tell you something more about or look at differences, how we can look at development from academic perspective and commercial perspective. And hopefully we will somehow manage to wrap it around to also connect with the POEMA, what we are doing right now. So also, sorry that I couldn't attend in person. About months ago, it all looked quite all right and everything was smooth. And now we are again with troubles with viruses and all that stuff. So hopefully next time. So the talk we named Bridging the Gap Between Academic and Commercial Software. And here is the outline of the talk. So yes, I will introduce the company, NAG, and then I will be talking about, in our opinion, what is actually the gap between development for academic purposes and development for commercial purposes, and is there anything where one can learn from the others? And we will look at it from the developer's perspective, and I will somehow try to put some experience from interaction with real users and somehow wrap it up somehow as a set of recommendations. And then we will have a look what we have right now and how this might shape the future, for example, with respect to NAG POEMA secondments. And that's the point where I pass on to my colleague Sean, who actually led these secondments. So he will talk more about this. All right, let's jump straight next to it. So NAG stands for Numerical Algorithm Group, and you might know NAG based on our main software product, which is the NAG library. So it's a library for numerical computational software for various numerical computations. So be it optimization, statistics, linear algebra, ODEs, quadrature, whatever you can imagine. And it's written in such a way that it doesn't have any particular targeted audience. So basically it's written in the math terms. So if you can formulate your problem as math, then in principle you could use our NAG library. Having said that, our main clients are coming from finance. That's far the most field where we are exposed. Then something like independent software vendors, where they take our numerical components and plug it into their software, but also academia and various other industries. Right now, the library has around 2,000 callable solvers or routines, and is available in many different languages. Lynn also mentioned that we are not doing just numerical software, but we are also quite exposed in high-performance computing, cloud, and things like modern hardware, for example, optimizing for GPUs. And the idea is here that, for example, if you have your application which runs on a supercomputer, if you parallelize it better, then ultimately you save costs because you save time on the supercomputer. And that's where NAG can help you. Another big field for NAG is algorithmic differentiation. So if you want to compute sensitivities of your code, or even of the solver itself, then you can use us. And if you ever program in Fortran, then we shouldn't forget the NAG Fortran compiler. So you should certainly try it. Now, what I will use as a motivation is actually history, how NAG started, because it gives quite nice lead to what I will be talking afterwards. So NAG was founded in 1970 as a collaboration between 4 universities, and the first NAG library was released in 1971. Now it's interesting to put it in a perspective, right? So it's more than 50 years ago. I haven't been born yet. My parents haven't met even yet. If you look at the computation, how it looked at that time, then we are talking about big mainframes. Personal computers came in the 80s. We are talking about punch cards because floppy disk didn't exist yet. And the main languages were something like Algol and Fortran. And also lots of things which we take nowadays for granted basically didn't exist. So for example, standardized IEEE arithmetics or libraries like BLAS and LAPEC, which lots of applications rely on. And in that way, NAG was founded because it was realized that lots of development has been done at the universities, but it's probably too big of a burden to expect that that the academics can take this for the final stage of the development, secure robustness, portability between the different systems, particularly at that time where lots of things were not standardized, provide documentation examples and robust testing. And of course, take care of the distribution and also user support. And this was really the moment. Now, if we scroll back 50 years later, lots of things have changed, but some stay the same. Right? So certainly there is much more in-house development than we did back then. But still, there is lots of academic collaborations. And we are pretty much faithful to the origins, where I would describe us that we are the halfway between academia and industry. And perhaps as a curiosity, NAG is set up as a not-for-profit organization, which means that any surplus goes back to research and development collaboration and sponsoring students and the likes. But the focus is pretty much the same. We focus on high-quality software and robustness and testing and documentation. But also, it is that we are not the end user of our own software, right? We are just providing building blocks so that others can start building application above them. So if you ask me if we have any polynomial optimization application problems, we don't, but we might have users in targeted areas where eventually this could be applied. So if I should summarize in one sentence what NAG does, it's about making numerical software more accessible. So now we can ask a question: what is actually the difference between, or is there any difference between development of software, numerical software, on academic and commercial basis? And I claim there is, because ultimately the motivation is most likely different. So for academic software, probably the main target is really just to validate the research. And anything above that is obviously plus. For commercial software, it's to create such a package which serves wide range of customers who are ultimately willing to pay for it. So the ways how we approach software will be different, but there is no reason why actually some of these things couldn't be used from one camp to the other. So let's start with us, developers, with the viewpoint. Now, when I was at university, there was no software engineering course at all. So people were self-taught. And I'm pretty sure that the system improved quite a bit. But I thought, anyway, what if we write down notes which I would class like what I wished I knew my younger self when I started the university. So let's start with how we develop, right? And I thought, okay, I should take an example somewhere. And it turned out that I don't need to go too far. I just scroll down to my old directories for projects which I was doing back then. If this looks anyhow familiar, then, well, listen further. Of course, I have no idea nowadays what's the difference between PenLab repo 2011 and 2011 old or temp uni or whatever, right? This all comes to how we store the source code, version control. It's not that I wouldn't be using repositories, but simply I wasn't managing the branches that well. So there were suddenly lots of versions floating around, which where you can very easily get lost. So what is version control? Well, I assume probably everyone knows it, but just for a reminder, it's a tool that you can easily track the changes, so you can see what has changed, when, and why, and by whom. It allows you to easily separate branches of your development. So for example, if you start bug fixing something, and it turns out that the bug is slightly harder than what you expected, and you have open changes, next to it, you can still do development on your stable branch. Or for example, your supervisor can have another branch where he is trying his own things. Right? You can easily go back in time. You can revert. So for example, if you are 2 days before conference and you are trying to regenerate the graphs, and suddenly you realize that your software doesn't work anymore, right? You can go back. So whatever you fancy, be it SVN, Git, or anything, as long as you and your team is familiar with it, then please use it. And now, it's not that people wouldn't be using it, but also I have seen cases where it was basically applied in the sense that we store the versions which we release, but the development was going on as usual, right? So surely, if you are using version control, you should do more commits than, let's say, once half a year. Okay, let's assume that we debug well, we have various versions, we use revision control. What comes next? Well, how can we know that if we change something, it doesn't break something else? Right? Or ultimately, if a user downloads our package, how does the user know that the package actually works? And this is all about tests. Lots of tests. This is the least glamorous part of commercial development. This is quite boring, quite time demanding. You need to write lots of tests, so it can be, depending on the complexity of the solver or the software in general, it can be a couple of hundreds of tests. Right? What's being tested? Well, not only the traditional input where we assume, okay, this is how it should work, but basically anything, different algorithmic paths, different inputs, wrong inputs. So basically, does the documentation matches with actually the behavior of the software? Now, this is probably too much to ask for academic environments to write all these tests. But I would still argue that there should be some tests. Right? Now, if you have probably more than, let's say, 5 tests, then you hit the problem that if you need to do it by hand and look at the results later on by hand, then you are probably not going to do it. Right? So ultimately, what's needed is some form of automatic execution and automatic analyzation of the results so that you get simply a result being the test fail or passed. And if you have this one, you can even automate this. And probably any commercial organization will have some form of continuous integration. So we use Jenkins, which is a free tool, and it's actually not too difficult to set up. So how does it work is that you have various environments, and this tool basically triggers the build on your behalf and gives you back the results from the analysis of the tests. And it's very flexible, so you can use it in different environments. But again, maybe this is slightly over the top. But the first thing is that actually there are some tests, be it at least a couple of benchmarks or something which should always run, which are triggered regularly when changes are made. So let's say that we have tests and it works on my machine. Now the question is, will it work if underlying environment changes? So it can be a different version of compiler, or you migrate to a different machine where the CPU supports different set. For example, Apple introduced new chip based on ARM M1. So will your code still work? Or if you migrate completely to a different operating systems, so you develop on Linux, will it work on Mac? Will it work on Windows? If you are using any underlying libraries or software like MATLAB, does it work across the versions, or are you relying on something which was very specific to a given version? Well, if you have tests, then it's obviously easy to go around and if you have access to the machines to try it. right? And this is what would be normally done in commercial environment. Last, what about distribution and licensing? So there is no right or wrong in terms of distribution. Should it be open source? Should it be closed source? Well, that really depends only on you, right? If it's open source, then you probably need to spend more time on the development of actually the build system, that it's easier for others to build a package. If you decide that it should be closed source, well, then you need to be careful that you support all the typical environments with different compilers and different settings. How you store the code and how you distribute it, well, is it just group level on the server which you maintain by yourself, or university level, or do you go fully public, for example, that you put code on your GitHub account? Well, it really depends. The problem is, if you maintain the solver by yourself, what can very easily happen is that one day the solver might crash and you might lose your repositories because you might not necessarily back up the solver the way as, for example, it's done on GitHub. Now, license is, in my opinion, often overlooked. And one message should be clear: if there is no license at all, then no commercial user will ever touch the code, because simply there is no way they can know if they can use it and under what conditions they can use it. So please use a license. Now it's up to you if you choose something which is fairly permissive, like BSD or MIT, which are very open, very easy to understand, and allow, for example, commercial usage of the code, or even closed sourcing. Or if you use something stricter like GPL. Now, if you are developing components which are more likely to be used in bigger applications, then probably things like GPL, licenses like GPL, might be a little bit restrictive. And again, commercial environment might not be able to use it because simply they cannot honor the terms of the license. But ultimately, it's about you, how you want to protect your code and how freely you want to give it away. But the truth is that a good license will allow potentially second life or third life of the code. Once your interest might move on, someone can branch the code and continue the development. So choosing a good license is important. So we covered so far the development side. We have code which is maintained, which have tests, hopefully is portable, hopefully is well distributed with reasonable license. And now it comes to the other part, the user. Now, when I started working at NAG, this is one thing which probably surprised me the most, because I assume that there is certain level of knowledge in optimization that basically everyone must know this, right? But if you start talking to real users, you might find that it's not so obvious what users know and what they don't know. Because ultimately, if you want to apply your software to a wider range of groups, well, ultimately you will find people who are not so skilled. But this is something what we should expect, right? Because ultimately the users are specialists in their own area, not necessarily in optimization. So these are a couple of examples. I put 3 examples of real interaction with users, how it can look like. The first one I called more optimal solution syndrome, and it can be produced in many different ways, but ultimately it's about, oh, I run your software and I don't like that particular solution. Or, for example, your software reported that the problem is infeasible. So what is the solution? I might not like the solution at the boundary. What can I do? And it's all around the same, that it's actually not well understood necessarily what the technology can deliver and what is actually a solution. Let me give you an example. Here you can see a nice smooth function. Okay, it's not convex, which we want to minimize over a given box. Now, if you ask people how many solutions they see or what they expect that the solver would give them, they might tell you, okay, the global minima over there in the front, fair enough, or some might say the local minima around as well, fine. But not many people would realize that there is actually a solution in the corner as well. The plane is slightly angled, and given the constraints, the solution in the corner is perfectly valid. So if you actually run solver, and if you are unlucky enough, and maybe I think we need to disturb slightly the derivatives to reach this particular path, but you can actually end up in the corner, and that's a solution which users might not like at all. But it can happen. Well, and as I said, the main issue is what is actually a solution, right? From the perspective of the solver, this is perfectly valid and is equivalent to any other solutions. From the perspective of the user, it might not be, because he wants solution for his business problem, not just a local solution of the real model. So for example, if they wanted to be close to the solution, maybe they could add some form of regularization, right? And maybe they could end up in the solution what they wanted. Ultimately, writing a correct model is hard, but it's essential. So if users might need to add some form of constraints because they don't like certain results, well, maybe this is perfectly valid, right? Nothing wrong with that, but they should also consider if their objective function is defined correctly. Do they get what they actually wanted? If they over-constrain the model, only they can know which parts of the model they could relax. The solver is, in that case, relatively innocent. It cannot help you. Another example, convexity. And if I show you this example, you will probably immediately know what I'm going to talk about. So imagine a reasonably nice quadratic function. That's the green thing, which we minimize over quadratic constraint. But here, the quadratic constraint is written as equality. So if we project the feasible region, you will get the Pringle-like shape red curve. And now what happens if we run our optimization? Let's start at this point and we run whatever your favorite local nonlinear programming solver. What happens is that actually you might end up there where you didn't want to be. But again, we are back at the beginning, right? This is perfectly valid solution. However, in this case, the problem was that the feasible region was non-convex. And in this particular case, if you just relax the feasible region, and you can know for this particular case that the solution cannot be inside, then you would get the global solution without any problems. But users might not be aware of that. Or if you are talking about anything with portfolio optimization, you might came across a Sharpe ratio function. You look at it and you can see that it's non-convex. Now, it's well described that this function has nice properties. So there is a simple trick that you can actually turn it into a nice convex problem. But still, lots of people might not be aware of it, and they might just take this function and pass it to the solver as a black box and see what happens, and then complain if it doesn't necessarily work the way as they want. And finally, making things unnecessarily harder because users might want to make it easier for themselves, right? And this is all about choosing the right solver and potentially exploiting the structure. If the user wants something like stable solver or performance, you could expect that they need to pass some additional information to the solver to help the solver, because there is not just one solver which will solve all the problems. Again, one problem from practice. Imagine that someone wanted to solve AX equals B over a determined system, so they decided to solve it in one norm. Now, someone could say, okay, this is nonlinear programming problem, so let's pass it to nonlinear programming solver, right? Luckily, our solver was not that, and he read on the Wikipedia, this problem is better to solve with a change of variables and solve it as linear programming problem. So he write it this way. Well, there is nothing wrong with this. And then he said, well, my matrix was dense. It was long and slim. So I will use dense solver. And then they came to us and complained, why is it so slow? But what he didn't realize, and you probably know already, if you write correctly the matrix, which is being passed in the solver, the matrix is perfectly sparse, even for this dimension. So if you run sparse solver, suddenly you will speed it up by 2 orders of magnitude. And actually, there is even a dedicated solver in our library, which solves exactly this problem. So if the user looked for the original problem, he would find the dedicated solver and he would save himself all the hassle. There are many forms of structures. Again, this is something what probably every optimization person knows, that if you have nonlinear least squares and if you have first order information, then using something like Gauss-Newton gives you a good approximation for the second order information. So actually, if you most likely use nonlinear least square solvers, it will work slightly better than if you use a generic solver for nonlinear programming. And below there you can see, or a set of benchmarks, how it might help. And sometimes it's significant enough. So yes, the first step should be actually to try the nonlinear least square solver. Again, there are many forms of structure what people might want to use. Now, can we somehow summarize, given this viewpoint on the user, what we might want from the user, how we might help him? Well, so first of all, the user, as I said, might not be expert in optimization. He might not even follow the trends in optimization. So what's new for you might not be new for him. And he will prefer the easiest solution which solves his problem. So if we don't want that they are using something like genetic algorithms and something very generic, we need to help them. If there is need for reformulation, can we do it somewhat automatically? Can we help them with scaling or anything in that form? So what would be the question, what I would like to be answered when I look at any package? Well, ultimately, why should I bother this package? What it can and cannot solve? Is there any limitation in terms of, for example, dimension or special properties of the system? For example, we had collaboration with University of Oxford for randomized least squares. And it worked well, but one thing which wasn't mentioned well enough for the users was how big the system actually needs to be, that this approach is much better than whatever other approach is. Can we say when and why one is preferable over the other? And if you have any special requirements, for example, that you depend on a particular library, can we write it down already at the beginning to make it clear? Ultimately, if there is new technology, we need probably more work to convince people to adjust to that. It's like chicken and egg. Is first chicken or egg? Is it first model from the user or the solver? Well, in general users probably need to know that the technology exists and is mature enough before they start building their models that way. So in this case, it would be certainly the solver and the supporting material for the solver to convince people to do it. So how can we help users to get started? Well, again, there is no miracle. Ideally, we want easy and clear installation instructions. So if you depend on particular language, compile a system, whatever, can be write it down. As I mentioned at the beginning, if the user manages to build your package, is there an easy way how to test that the package actually works? Some basic set of tests or something like that. Because if he starts messing with this, he should be sure that actually something works. It's not. It's most likely his fault why it suddenly doesn't work, rather than some misunderstanding how to build something and why it's crashing. Can we help the user to start? So can we provide example which he can modify to play with, or a tutorial, or of course correct documentation where we well describe what the inputs and outputs are, what can happen, what could be errors resulting out of it, and ideally also an advice how can we mitigate the error. Right? If we say, well, the solver didn't converge, can we give a better advice than, well, change your model? sometimes, not always. What else would be on my wish list? Well, intuitive interfaces, good error handling. The input should be well tested. So what I mean is, if you start with a certain package, it's not unusual that you mess something up. For example, you pass the matrix the other way around, or you mix some arguments. So really, it's not necessarily intention that the user would pass completely silly input, but it might be by accident. And yeah, the solver shouldn't just crash. And if it works with any atypical data, that would be certainly a plus. So does it do any particular scaling? Can it solve any edge cases? Does it have any clear output that people understand what's actually happening inside? That would be all great. So, okay, we covered what we would like. Now, if we look at what we have at NAG and what might happen in the future, particularly, for example, with polynomial optimization. NAG's goal is really ideally to reach the stage that we are the one-stop shop for optimization, that you can come and we have basically everything what you need. At the moment, we have lots of solvers available from lots of different languages. And I believe that we follow mostly the guidance what I just gave you quite well. But what does new actually mean, new solver? Well, as I mentioned several times, the users, the general public, won't be experts in the particular field. So something which is well established in the optimization community might not be so well established in the industry. So for example, with second order cone programming solver, I would say it's quite all right, but you will basically find two camps of people. One, where they very well know what second order conic programming is and how to handle it, and the others who never heard of it. Now, if we move to something like semi-definite programming, I think this is much harder to get people interested. Of course, there will be some models which directly lead to semi-definite programming, but typically you would need some form of reformulation or relaxation to be able to use it. And this is probably the culprit there. Now, for SDP, there is certainly, so for example, what we did is that we presented to various clients and models which we found in academia and which we thought like this might be interesting for you. But people were interested, but for example, there was not big uptake. So either they knew SDP before and they wanted it, or yeah, it was basically something to try at some point when we have time, which usually means not anytime soon. Okay, what about polynomial optimization? It would be beautiful once it reaches the maturity that it could be just another tool in the toolbox. Now, are we there yet? Well, I will let my colleague Sean to take over to talk about the secondments we held with POEMA. So thank you for your attention for now. Thank you.
Right. Hello, everybody. My name is Shuanghua Bai, and yeah, as Lin introduced, I'm also a software developer in optimization in NAG. So I've joined NAG like 5 years ago. Yeah, my special basically I'm a developer in conic programming. So let me try to share my screen to see if it's working on my machine as well. And sharing. All right, now to full screen. Right. So yeah, thanks for this opportunity, and thank you for the organizers to organize this workshop. And for the rest of the talk, I will be talking about the POEMA secondments we have with the POEMA network. So we have 3 secondments in total. The first one is with Tobias. We are looking at the relationship between non-convex quadratically constrained quadratic programming, non-convex QCQP, and the polynomial optimization. What is the bottleneck? Why polynomial optimization is not working on non-convex QCQP, and how can we actually improve it? And then the second one is about a more structured problem, which is called polynomial optimization, portfolio optimization problem, but with higher order moments. I'll come back in detail later in this talk. And the second one is with RFA. So we are testing a SDP solver, but to explore the low rank property for a special problem class called optimal power flow. I must say all three segments are hosted virtually due to the current pandemic and also due to the Brexit. But we've got a great support from POEMA network and organizers. So a big thank you to the organizers and all the hosts in the POEMA network. So jumping into non-convex QCQP, what we did is first, why not to try some solvers on some toy problem. Here is a non-convex small toy of non-convex QCQP. As you can see, you have a quadratic non-convex objective, you have some linear constraint, and you have a bound constraint, and then you have some non-convex quadratic inequalities. So we've tried small problems, like number of variables from 3 to 12, and then we've tried nonlinear programming solver, and we tried the state-of-the-art spatial branching and bound method from Groby, and we also tried polynomial optimization solver. And then, as you can see, without any surprise, the branch and bound from Groby is truly the state-of-the-art. So for small problems, it's basically solve it in no time. But for nonlinear programming, for some problems, it can solve to global optimum as well. But for problems, for example, the third one, it actually failed. It's stuck in a local solution, which is also expected. But we can see the polynomial solver is actually not that good compared to the other two solvers there. So yeah, so what we should do, so what we want to do is we want to move into a more structured problem as well. So now we are looking at, so there is still ongoing research to see how about we just consider a linear programming problem, but with some binary constraint there. At the end of the day, it's still polynomial. So what could this constraint impact the whole polynomial framework? So that's what we do. And speaking of the structured problem, if I can move to the next slide, yes. With Andres, we are doing research in portfolio optimization, but with higher order moments. So a general question in portfolio optimization is, given a certain data set and you can calculate some statistics, how do you actually select the best asset allocation to achieve the best portfolio performance? So there are many measurements on the performance, and I will touch them later in the talk. So this table shows a example of what data set could you get. It's basically a historical closing price for 10 stocks in the market from like 30 years ago. For example, the first column is basically time series of prices. For example, first column, Apple, GE, AMD, etc. So the basic model in portfolio optimization is to model the log price as a random walk. So at time t, the price or the log price depends on the price from the previous timestamp plus a drift constant mu, and also it's related to a random disturbance or random error, which could have mean zero and some other distributions on the variance. The right-hand side is just a plot of log price of Apple for the past 30 years. As you can see, the log operator there actually linearize the price a little bit just to remove the exponential growth or decrease or increase from the price. And the right-hand side is a autocorrelation, just to prove that it's kind of a random walk. As you can see, for lag 1000, at timestamp t, with lag 1000, there are still some correlation or relationship between those prices at those timestamps. So indeed, the log price is random walk, which is very hard to actually predict anything. And what we should do is look at the asset return. So there are many ways to define the asset return. For example, you can calculate the direct change, percentage change, or you can calculate the log return, or you can use the factor models to just relate each price to some set of factors, and then you can just estimate the factor loading beta ij, or the expected return of the factor alpha. And also you have some error term there. So if you plot the return there, as you can see, the returns are actually stationary. From the autocorrelation is also a proof saying like there is actually no dependency on different time steps about the net return or log return or factor models. And one, excuse me, so one of the most fundamental assumption in modern portfolio theory is that we say the return follows a RAD distribution, which means actually we can drop the time index t here. We say the return of one stock is a random variable follows some kind of distribution, which can actually be modified, or sorry, be estimated or be modeled. This is a key contribution from Harry Markowitz from the 1950s, who is also a Nobel Prize winner for his contribution in this modern portfolio theory. So what parameters can we actually estimate, or do we need actually to estimate? So the first is the mean, or the expected return of each stock. You can just do it by the sampling mean, or you can use some weighted mean returns. You can give more weight to the most recent prices data. And also you can use capital asset pricing model, which is basically a factor model with just one factor, which is the market price. And also you need to estimate the covariance matrix, which is a measurement for the risk. You can do it via the similar thing, via the sampling. You can give exponential weight to the covariance matrix, or you can use some other matrix to do shrinkage on the sampling covariance matrix. And then the model becomes the following. So we have two objectives to consider. On one hand, we want to maximize our return or expected return. On the other hand, we want to minimize the risk measured by the volatility. And then we still have some special needs, and therefore we have some we have some constraints. I'll come back to the constraints in the next slide. So to tackle these two multi-objective problem, there are many ways. The first is actually you can just minimize, in practice, you can just minimize the volatility or minimize the risk, and then you set a lower bound on your expected return. And in practice, because the expected return mu is really hard to actually estimate it, some people even just drop the performance constraint, this mu transpose x greater than or equal to R mean, to just minimize the risk. And then they try other ways to diversify their portfolio. The other way includes, for example, you can maximize your expected return, but set a upper bound about the risk. So I don't want my risk to exceed some certain amount of value. And the second model is called the efficient frontier. So it's a trade-off between your return and risk. So if you move lambda from 0 to a very big number, you will get, and you draw the actual return and risk, you will get a efficient frontier. I'll show you example in the next slide. And another measurement is you can maximize some kind of ratio. Here I'm saying that I'm writing the basic Sharpe ratio here. It's basically a ratio between your risk and your return. And also you can use, if you don't want to consider the interest-free return, then you will have an information ratio, but the technique is the same. And also you can have many extensions here. For example, you can use different risk models. for example, you can use value at risk or conditional value at risk to modify, to model the tail of your distribution, and then you don't need to consider the volatility solely. And you can build robust optimization to tackle uncertainty in your data. For example, here you don't know mu, but you know a uncertainty set of mu where mu should be in a interval, and then you just maximize the worst case scenario against the uncertainty set of mu, and similar for sigma, which will basically end up with a SDP model. And also, you don't actually need to build covariance matrix, and you can do it via simulation. So some words on the feasible region, you could have some practical constraint as well. For example, you will have some budget. So I will only have £1 million to actually invest, for example, and you can have sector exposures. For example, I want my investment in defense less than or equal to like 20%. Or you want to diversify your portfolio, you will have a maximum position. You'll say like the biggest investment should not exceed, for example, 5% of my capital. Or you could have leverage. This is called 130-30 rule. Basically, you can sell short 30%, which means you can have negative portfolio weight by 30%, and then you will have 130% to spend. And also, we can take the transaction cost into account, because trading, there is a cost in the trading. For example, this market impact cost means if you trade a large amount, it will actually impact the stock price in the market. Also, some tracking error, which is quadratic, and cardinality constraint, which means the number of non-zeros in my portfolio should not exceed K. So maximum K stocks I want to buy. Most of the cases mentioned above can be solved via conic programming. For example, second order cone or SDP. And if they have like cardinality or either/or constraint, their logical constraint there, then you need a mixed integer version of SOCP or SDP. And here is an example about solving the efficient frontier. Let's focus on the blue curve. So this blue curve is called efficient frontier. The x-axis is the absolute risk, and the y-axis is the return. So we call it efficient frontier because for a certain risk, let's take a look at this black square here. If you lower the expected return, you could still have the same risk. So for the same risk, you will always push your expected return up until you reach the efficient frontier. And then this black square is called Sharpe ratio. Is called the most efficient portfolio, which basically maximize your Sharpe ratio there. And this is calculated without the tracking error. As you can see, if we have a benchmark, which is marked as star here, you can actually set a tracking error, which is a quadratic inequality, to actually bring your most efficient portfolio closer and closer to the benchmark. This is an example about how to solve classical portfolio optimization via conic programming. But there is actually there is a practical extension for the mean variance or the Markowitz model. This is to consider the higher order moments. Why? Because the classical mean variance models assume the return to be normally distributed, which is true for the continuous time period. But in practice, the time period could be finite, which means it's a discrete space. And there, the normally distributed portfolio returns is not adequate. And also, the mean variance models are found to be unreliable because it actually maximizes the estimation errors. As I said before, the expected return mu is actually very hard to estimate. So if you use the previous mentioned model, it could actually maximize that error resulting in bad performance. And so what we need to do, we want to actually take consideration for higher moments, for example, skewness and kurtosis. This is to just strengthen the risk management. So what is skewness? Skewness, as you can imagine, as you know, that the normal distribution is basically asymmetric distribution, but skewed distribution looks like that, looks like this. So on the left is we call the left skewed or the negatively skewed distribution. As you can see, there is a very small probability that a very bad thing happens. But for the positively skewed distribution, there will be a slightly higher possibility that a very small loss could happen. So in risk management, what we really want to avoid is the bad surprise, which means a low priority, but you will lose a lot of money. So this is what we want to actually avoid. So therefore, we want to minimize the we want to maximize the skewness as large as possible. And also we want to avoid the heavy tail, which means the extreme cases. The heavy tail means the extreme cases will have a very big probability to happen. So this is what we want to avoid. So we want to minimize kurtosis. If you take consideration of skewness and kurtosis, the multi-objective problem becomes as follows. So the first two is the same thing from mean variance. We want to maximize return, minimize the risk, but we also want to maximize the skewness and minimize the kurtosis, which means in the objective, we will have cubic and quartic objective functions. This is where the polynomial optimization can kick in. A natural idea, because it's multi-objective, first we need to construct something actually we can work with. So the natural idea is follow the mean variance model. We form a linear combination. We choose some linear coefficient to just construct one big objective function. But then there are scaling issues, which also results in the difficulties in choosing the correct lambda to incorporate the preference on all these four statistics. And in the literature, there is a well used framework called Go programming. So this is a very fundamental approach to tackle the multi-criteria optimization problem in operational research. So the polynomial Go programming framework is first introduced by Tai and Leonard in 1988. So they were trying to solve some balance sheet management problem where you have some competing and conflict objectives. So the framework applied for our case should be, we first calculate the optimal solution of all four individual optimization problems. As you can see, to solve F3 and F4 is already difficult because they are polynomial. And then if we can solve those, or we can have a relaxation or approximation to all these F stars, we can construct using the modified Minkowski distance to build our utility function, which is a very big polynomial optimization problem again. And we have and also we can include some of the practical constraint as well. So yeah, as I said, the polynomial Go programming is one of the earliest practical techniques to tackle the multiple criteria decision-making problem. And we're using it because it's empirically tested on stock, index, and hedge fund portfolios. So in the literature, it's proved actually it's kind of working. That's what we know. And it can well incorporate the portfolio manager's personal preference. And those preference parameters, all those lambdas, are actually studied for various markets. For example, people know for US market, the lambda for kurtosis should be larger. And then when we solve our problem, we can set the parameters to our needs. So this is also ongoing research. what our goal is, what we are doing is basically, or Andres is doing basically, is we want to relax and reformulate the problem into Polynomial optimization problem, which is basically some weighted sum of exponential functions. And there, the conic programming can be used again, because Polynomial optimization relates to the exponential cone solvers. There we can have a lower bound, and then because NAG has a great selection of nonlinear programming solvers, be it SQP solver or IPM solver, and also we have 2 global optimization solvers using multi-start and particle swarm algorithm, so we can actually solve it locally to get a lower bound. So now we're analyzing the quality of lower bound and upper bound to see whether we can actually solve the problem approximately and whether the result is useful or not. And also for the cardinality constraint, if you solve the cardinality constraint via mixed integer programming, it's a problem to solve. But if we have cardinality constraint, maybe this constraint actually can reduce the complexity in polynomial optimization, because it can reduce the space, the big search space, to a smaller ones. So this is also ongoing research, and we are at the end we will do backtesting using the real world data, and also we will test on the scalability, like how many assets can we actually solve via this technique. That's basically what I want to say. So yeah, thank you, and we are happy to take any questions.
All right, thank you very much. I will first turn to the physical audience for questions, and then I will then ask people from the remote audience to kind of turn on their mic simply when they want to ask a question. But first, physical audience. Okay, we have Didier Henriot first, who would like to ask a question. Maybe you can say to whom you are going to address it.
Yes, maybe it's a question for Jan Fiala, who spoke about SDP in NAG. And so I'm curious about the current situation of SDP solver in NAG. Is there a solver which is currently developed, and which algorithm is it based?
Okay, this is easy to answer. So this was actually one of my first tasks when I started at NAG, and it was to develop a SDP solver, and the algorithm what has been used is the same was being used based on Michal's Pennon. So it's generalized augmented Lagrangian.
Okay, thank you. And you said that there is limited interest of customers and industrials in SDP. Can you say a little bit more? So they try and they're disappointed, or they don't even want to try?
I think this somehow depends on the target audience which we were trying. So as I mentioned, our biggest exposure is to finance, and when you look for applications in finance for SDP, then there are some. So we were presenting them, for example, something like robust portfolio optimization or something with option pricing and things like that. But yeah, the uptake was very limited. So it's not that people would even reach to the conclusion that they would want to test it and use it for their model. So from that perspective, it was a bit disappointing. So basically, either what I was trying to say was that it seems to be difficult to convert people who don't know it already to actually use it. To me, I would simply say it's too new and advanced technology for ordinary people. This sounds a bit silly, but maybe you know what I mean.
Jan, can I ask a related question to that? Do
Sure.
you think it's really because of the novelty or because of availability of phase solvers for SDP?
From the reactions what we have, I think it was more the novelty, because the answer wasn't, oh, we are using, I don't know, SDTP3 or Sedumi. It was more like, okay, this sounds interesting, but we are too busy to try it. But again, like this is limited audience, right? Probably in different fields where this is more applicable, it would be more interesting. But it was a little bit disappointing. And this is something which we still need to try at some point again, to basically show how it can be used and that it's actually pretty powerful. Yeah, but somehow if you read any academic papers about SDP, you have the feeling how great technology and powerful technology it is. But then when you go to practice, at least again from the experience what we had, it was quite opposite.
So do we have, yes, Andreas, please?
Question for Jan with regards to insight into what the customer expects from the optimization. Like, give us an idea of.
Sorry, I can hardly I can't hardly hear. Can you speak a bit louder, please?
Yeah, he's going to come closer to the microphone.
Oh,
It's close to the microphone. Right. So with regards to customers, so it sounds like you have a bit of a difficult situation because on the one hand you have to educate people into what optimization is and what it can do for them, and at the same time sell it to them. So can you give us an idea of who is like the general customer who would come in search of optimization solutions? Is it a big company? Is it a giant company, or can there also be like small businesses and maybe like individual vendors?
It depends. I assume I won't give you any company secrets if I say that NAG is probably exposed in something like 70% of tier 1 bank investment banking, where basically they use the technology in their quant libraries and it's embedded inside. And this is far the biggest customer base what we have. Yeah, but there will be different ones. I shouldn't name any particular ones, but like, yeah, it can differ. It can be like one person license, or it can be global license for a global company.
Okay, so there's no fixed constraint, but in general, it's an expert representing a company coming with a need.
Yes, at the moment, I think typically how people find NAG is that someone has particular problem and is looking for the solver which will solve the problem, and knows actually that he needs, or thinks that he needs, this particular solver and looks for it.
Okay, cool. Thank you.
Monique, did you have a follow-up question? I see you turned on your camera. Your sound is off. We don't hear you.
Thank you. It was a question to Shuanghua. So maybe I first leave the word if somebody wants to go on. So maybe I can ask a follow-up question. So the customers didn't want to try it or were not interested. And it was not a question that SDP is not so well developed to solve big problems. It was not even that issue.
Yes, it was basically like, if you imagine, particularly if you talk in finance, like everyone is busy, right? Who is not busy? So if you say, yes, try this new technology, it might bring you some benefits. Unless they see clearly the benefits, what it does for them, they are simply, in my opinion, too busy to play with it, right? Because they have their own list of things they want to try and test. So yeah, it wasn't that they would get to a trial and they would say, okay, for our problems, the technology is not mature enough that it doesn't work. It was simply they didn't see the benefit of applying it. They didn't see that tempting application to actually go for it.
But wouldn't you be worried that maybe they try and they have problems which are too big and anyway they fail?
Well, to be honest, if we reach that stage that we have people who say we want to use it, but it doesn't work, then we are in better position, right? Because we can hopefully get some of the problems and we can look into it, what we can do about it. Like, is there anything how we can help that the problem works? It's the same as with any other support, right? If someone comes and say, I can't solve your problem, then we can have a look at it, and often enough it is, okay, we can fix either the solver or your problem so that it works. So, of course, fixing SDP solver might be much harder than it sounds like for adjusting some small things in the model so that nonlinear programming works. But yeah, it would be nice actually to be in that stage that you know that there is demand and that generates further action on our side.
Thanks.
We have another question in the room. Yes, so Jean-Max is also.
I'm Jean-Max from RTE. Recently, RTE, we started about 2 years ago with Linux Foundation Energy for software components for platforms, for software, for grid studies, or business of electric grid. So the business model is Linux Foundation Energy. So the idea is that we hope to share development costs with others, like it was made in telecom or 5G, as I was told. So it's a different business model as yours in NAG. So would you be ready to go to something like Linux Foundation or not? First question. And second, if you were to start NAG today, not 50 years ago, but today, would you choose to business a model as a non-profit company you are today, or go for free software foundation?
Why? Okay, well, this would be more question for my boss's boss than for myself, right? I think in principle, the not-for-profit setting is not actually too bad, right? Because what it means is that basically you just ring fence the benefits what are coming from the company, that they cannot be spent other than, for example, in research or in collaboration. So that's not too bad. Now, in contrast to free software foundation and be completely open source, well, that depends, right? Because even now, some collaborations are done in such a way that we have code which wouldn't be open source otherwise, but we financially support the developers, and in exchange we have the code. If it was completely free, then of course you can make completely different business model, which might work as well. It's hard to say, but yeah, I think for the way how NAG was set up, it wasn't a stupid idea at all, I think. Oh, does it answer the questions at least partially?
I think there is no real answer to really speaking about this. But there is no true or false. I mean, 50 years ago, free software or something like Linux Foundation did not exist. So, so your company now is something marvelous. Okay, that's not easy to. If we start something like you today, what would be the best choice? That was roughly my question, but you give your ideas.
Yeah.
All right. Okay.
So I have a question.
Introduce yourself.
I'm Milan Korda, and I have a question on the second speaker regarding the second man of Tobias. So there, what is exactly the goal of looking at the TCP piece? Do you want to improve the polynomial optimization there, or can you comment on it a bit more?
Right. So the purpose of the segment is just to explore the possibility to solve the non-convex QCQP via polynomial, because as we know, the branch and bound problem, branch and bound method is working pretty well for the problem already. But we want to look at the problem from a different angle, to see whether polynomial optimization can do something on that problem as well. If it's not general problem, we want just to solve mixed binary linear programming. It's actually double direction. It's either polynomial can improve mixed binary linear programming, or we can improve polynomial optimization from a branch and bound method.
Okay, and are those examples that you looked at the only ones, or did you look at also larger example and maybe structured ones?
Yeah, we've tried a large data set, but for polynomial optimization, the big problem is really hard to solve. Therefore, we just listed some small problems just for illustration. But for big problems, yeah, the branch and bound works really well, but the nonlinear solvers will stuck at local solutions in a lot of cases.
Right. So the branch and bound, you say that it can solve problems with how many variables?
I think for non-convex QP problem, for example, so all the constraints are actually linear. They can actually solve thousands.
The global optimum.
Yeah, to global optimum.
So since we spoke about binary optimization, I think we should give the microphone to Monique Laurent, who might have a question around that. Monique?
Thank you. I just wanted to ask a follow-up question on this. It's just for my understanding. So you said that polynomial optimization doesn't work. So what do you mean exactly by that? So you are solving the moment or the sum of square relaxations of a given order? Is this
Yes, we were trying basic we were trying open source polynomial solvers. That's the only thing we did. We didn't actually develop any polynomial algorithms.
Okay. Okay. And did you test the flatness condition?
No.
It's maybe part of the software, and I think it's in Globtic Poly, or in several software it is.
Yeah, I think Tobias actually tested glib poly. Yeah, but what we do is basically we take the data and we feed it into the solver, and yeah.
But what does it say to say? What does it mean to say it doesn't work compared to nonlinear program optimization, because you're comparing two different things, huh?
Yes, we're comparing the accuracy first of all, and then the computational time. So basically, it took too much time to solve.
But in general, with the global polynomial optimization, you don't get a point in general. So you just get a number, a value.
Yeah,
no?
just get yeah.
So you compare the value with the value of the point you get with a local optimizer.
Yeah, yeah.
So, okay, but which are different things, huh? Because you get with polynomial optimization, you get a lower bound. And with a local optimizer, you get an upper bound. So how do you compare these things?
We just compare the difference, between those bounds and the actual global optimum.
Oh, okay, because
be it the lower or upper. Yeah.
Oh, okay, because you have problems where you know the optimum solution. Okay.
Yes.
Oh.
Yeah.
Thanks.
So just to follow up to that, you solve the higher relaxations, not just the first order relaxation with the polynomial.
Yes, we were trying higher orders as well. So second order. But yeah, if you use higher moments, then the computational time is really.
Yeah. And the problems were dense or sparse? Do you know?
It's sparse.
Sparse. Okay. Then maybe.
Okay, I think that Didier in the room also wants to follow up on that, I think.
Yes, you mentioned that Gurubi branch and bound algorithm can solve problems with thousands of libraries, but which guarantee do you have on the quality? What guarantee do you have that it's a global minimum?
Yeah, that's true. I think that's tricky to answer because according to the documentation, Gurubi actually size is global optimum. but
You must
we don't
trust
know
the
how.
documentation, or you don't have any other piece of information to certify global optimality?
I think from the log, they actually computed some bounds because it's branch and bound. So they are actually computing the gap between your Primo and you. And when they see actually the gap is approaching, you know, a lower tolerance, then they declare the optimum.
Well, yeah, not that I would want to do advertisement for our competitors, but yes, it's basically some form of spatial branch and bound approach where you can do linearization of the constraints, and basically you can get guarantees that it's not just something like let's multi-start nonlinear programming or something like that. It gives you the global solution, and surprisingly it works fairly well.
Okay, Michel Cabrera, that will be the last question maybe for this session, or so that we can have a little break, but we will be free to kind of ask for meetings, private meetings afterwards. Okay, Michel? No, you have your sound off. You have to start again with the sound on.
Sorry. Just a comment to that. At least my experience with Grobe is that it may work very well, of course, faster than Polynomial, but it's quite sensitive to even a small change of data. Sometimes you need 100 iterations, sometimes 10,000 of iterations. While Polynomial, you solve the SDP of the same size, and the behavior is sort of independent of the change of data. So the interior point algorithm just works as well. So the robustness may be on the, if you make it faster, then the robustness could be an advantage of polynomial optimization.
Yeah, I can imagine. I should state, like, the tests were done by Tobias, right? Because we don't have access to the license directly. So it was done just as part of the secondments. And there is certainly probably more how we could play with that, try different problems and get the sweet spot, like what type of robustness we can find that polynomial optimization wins over spatial branch and bound. But, well, the time was limited.
All right, with that, I think we will stop. I think it was a very interesting discussion. So thank you very much. Thank you both for your talks.